Assalamu alaikum, dear student. This is lecture number 3 of week number 7. So we are continuing the chapter number 7, dimension analysis. So let's see the topics we are going to cover of this chapter, dimension analysis. So today the topics we are going to discuss, first of all we will do some practice problem of dimension analysis. Then we will see the heading uniqueness of PyTerm and common dimensionless group. We will see correlation of experimental data. Okay, so let's start and do some practice problems so that we can fully understand how to solve the problems by using dimension analysis techniques. So here you see there is a problem. Water sloshes back and forth in a tank as shown in figure. The frequency of sloshing omega is assumed to be a function of the acceleration of gravity. The average depth of water h and the length of the tank is L. Develop a suitable set of dimensionless parameter for this problem using G and L as repeating variable. Okay, so here also the repeating variable is given, okay, and the variables are also given. So let's see, according to the steps to solve this problem we know very well. So first of all, what normally we do, first of all we note down the what are the total number of variables, including the dependent variable and independent variable. Okay, so so here what are the variables? Variable number 1 is the omega, okay, the frequency, and the gravitational acceleration g, the length d, and height h. Okay, these are the 4 variables are given. Okay, so here you see the total number of variable is 4. Okay, and after that what we normally do, we find out the total number of dimensionless group involved in the, or total number of fundamental dimensions involved in that, in those variables. So here you can see this is omega. Omega is basically the frequency, so the unit of frequency is 1 over time. Okay, so this is T inverse, the velocity, the fundamental unit of omega. The gravitational acceleration L over T square, the length is L, and the height is also L. So here we have 2 variables, one length and other is time. Okay, so that means the total number of basic fundamental dimensions are 2. Okay, or the total number of reference dimensions are 2. Okay, so here is the 4 minus 2 is equals to 2. So that means only 2 dimensionless groups will be formed. Only 2 dimensionless parameters will be required in that case. We can reduce 2 variables in this case. Okay, so here use G and L as a repeating variable. So now next, once you find out the number of dimensionless group, so after that we start forming the first dimensionless number. So how do you find the dimensionless number? The first pi term, in the first pi term we multiply one non-repeating variable with the repeating variable with exponent power. Okay, so your G and L are the repeating variable and it has exponent power, and we are multiplying with the first non-repeating variable omega. Okay, so here we replace the value of the fundamental dimensions in variables. So here we replace omega with t minus 1, gravitational acceleration lt square, lt minus 2 square, or the L is the length. Okay, So here this is the dimensionless number, okay, because the pi 1 is the dimensionless number, so we replace with dimensionless number. So we equate the power with respect to L and T, and finally we got the value A and B, and then we put these values back in this equation, and finally we got the first pi term, which is omega under root L over G. Okay, now we have to cross check. To cross check, we have put the values of dimensions back in this pi term that we have derived. So here finally when we solve all the dimensions, so we end up with L naught and T naught. So that means this is dimensionally this relationship is possible. So now let's move on to the next pi term, because we have to make two dimensionless parameters. The first dimensional parameter we found it this. Now the second pi term, how we can develop the second pi term? The repeating variable g dot a dot will multiply with another non-repeating variable. So what is the another non-repeating variable is remaining? That is h. Okay, so this is going to be multiplied with the another repeating variable, that is h. Okay, so again we will replace all the variables with their dimensions: height L, G L T minus 2, and L is dimension L, and again we equate the exponent power. Okay, and finally we got the values A is equals to 0 and B is equals to minus 1. Okay, so we put these values back into this equation, and finally we got the second pi term, or the dimensionless parameter, which is equal to h over L. Now we have to recheck whether it is this relationship is dimensionally possible. So definitely this is also L, this is also L, because the dimension of the height is L and dimension of the length is also L, so they cancel each other. So this is dimensionless parameter. So we can write down omega under root L over G is a function of h over L. Okay, so this is the relationship we have found. Okay, and here these are the two dimensionless parameter where omega is depending on these height h and length of the container. Okay, so this is the relationship between the variables involved in this problem. So let's see another practical problem, and there is some another thing that you will learn. Because of that I have considered this problem, so that you can understand how to solve the dimension, how to solve the problem related to dimension analysis. Okay, so here determination of pi terms again. So here there is a problem: an open cylindrical paint can having a diameter d. So you all are familiar with this cane. Okay, okay, for the paint. So it has a diameter which is given d, is filled to a depth h. The paint is filled up to the depth h. It is not completely filled up to the top, it is filled up to this height h. Okay, with paint having a specific weight gamma. Okay, so the specific weight of the paint which is given is gamma. Okay, so the vertical deflection gamma of the center of the bottom is a function of d. Okay, so here this is the deflection. Okay, this is the vertical deflection. Okay, so this is you can say it is delta. Okay, this is indicating with the symbol delta. Okay, so this is given a small delta of the center of the bottom, is the deflection from the center of the bottom. Okay, is a function of diameter. Okay, so here the function of diameter delta is the function of diameter h, d, gamma and e. So where d is the thickness of the bottom, so the bottom plate has a thickness. Okay, and E is the modulus of elasticity of the bottom material. So the more thin and more soft is the bottom material, so the more would be the deflection. If it is more strength, more thick, the deflection will be less. It can hold the specific weight of the paint more strongly. So we have to see, we have to develop a relationship between the diameter of the we have to develop a relationship between the deflection and the diameter of the bottom plate, the thickness of the bottom plate, and the modulus of velocity of the bottom plate, and height of the paint stored in the container, and specific weight of the fluid contained in the cane. Okay, so that means this deflection is depending on these variables D, H, small d, gamma, and E. Okay, so I think it's clear. So now so now we have to find out a relationship between what we have to find out, determine the functional relationship between the vertical deflection and the independent variables using dimension analysis. So we have to find out a relationship between vertical deflection and the other variables which are depending at which this vertical deflection is depending. Okay, so the first step is to determine the total number of variable. So here it is given that small delta is a function of dH d gamma into E. The second step, to write down the dimensions of each variable. So the deflection normally we measure in length, diameter we measure in length, height we measure in length, thickness we measure in length. This is specific weight. Okay, so the specific weight in MLT system. So whatever is the system, this dimension will remain same up to here. Okay, so whatever is the unit, the dimension will remain same. And here you can see we have wrote down the dimension of a specific weight and modulus of elasticity in FLT system as well as in MLT system intentionally. Okay, so these four variables have a same dimension in both the system of dimensions, but the gamma, the specific weight, okay, the force per unit volume, and the modulus of elasticity, the force per unit area. Okay, so this is the unit in FLT system, and this is the unit in the MLT system. So first of all, we are going to solve this problem by using the FLT system. Okay, so let's start. So first we are going to follow this part. Okay, then we will come to this part. Okay, so let's see here where the dimensions have been expressed in terms of both FLT and MLT system. We now apply the pi theorem to determine the required number of pi terms. First, let us use FLT system. Okay, as our system of basic dimensions, there are 6 variables and 2 reference dimensions F and L. Okay, required for 4 pi terms are needed for repeating variables. So we can select D and gamma, so that, okay, so since we do not have since in all 6 variables we do not have, you can see all 6 variables, okay, in the previous slide, these are the all six variables. So we do not have any flow, we do not have any flow properties, only we have the geometrical properties and the material properties, but we do not have the flow properties. Okay, so since this gamma is related to fluid, so that's why we have considered this as a repeating variable. Okay, so here we are considering gamma and diameter of the cane as a repeating variable. Okay, so that you have to select yourself. Okay, so we have selected. So when we minus total number of variables, so we have 2 reference dimensions F and L. not the fundamental dimension, the reference dimensions. Okay, the fundamental or basic dimensions are FLT, but this is the reference dimensions which are explaining the whole variables. Okay, so here the first pi term, so what is going to be the total number of pi terms we will get in that case? So total variable we have 4, 5 and 6, and total number of reference dimensions we have 2. Okay, so 4 minus 2 equals, sorry, 6 minus 2 equals 4. So in this case we will have 4 pi terms. Okay, so the first pi term is multiplied by the repeating variable with the exponent power with one non-repeating variable. So pi 1 we have considered the first non-repeating variable is the deflection, the small delta, and that is basically a dependent variable. Okay, so we replace all those values with the fundamental dimensions, and this is a pi 1 is dimensionless number, so it is going to be replaced with the exponent power 0 and 0. So this is a dimensionless number. So we solve the power and we got the value of a and b. Okay, and we replace this value of a and b in this equation. Okay, so here b is equals to 0, that means gamma is going to be the 0, though, and the first pi term is going to be deflection over diameter. So you can cross check this. It has a dimension length, basic dimension it has length, basic dimension it has length, so it's going to be it is definitely a dimensionless number. So now second repeating variable multiplied with another non-repeating variable, that is h. So again we found the value of a and b. We replace these all variables with the basic dimensions. Okay, and we got the second pi term is equals to h over d. In a same way, okay, we solve the repeating variable with the third non-repeating variable, repeating variable with fourth non-repeating variable, and we solve their exponent power, and we got the final pi term values. Pi 3 is equals to small d over capital D, pi 4 is equals to modulus of elasticity and the diameter and specific weight. So these are the 4 pi terms we got it. So since this pi term has a dependent variable, so the pi 1 is a function of pi 2, pi 3 and pi 4. Okay, so pi 1 is a function of pi 2, pi 3 and pi 4. Okay, so in that case, so this will be our answer, or this is basically the combination between the variables involved in this problem. Okay, so let's see if we solve this problem by using the if we solve this problem by using MLT system, then what will happen? Let's see, go back to the basic dimensions here. You can see here, so we have how many variables? We have 1, 2, 3, 4, 5, 6. We have 6 variables. So if we consider we are going to solve this problem by using MLT system, then what will happen? Here you can see in MLT system, dimension of deflection is L, dimension of diameter of the cane is L, height of the liquid is L, thickness of the bottom plate is L, and the specific weight is equals to weight over volume. So you replace the weight is a force. So when you replace force in the form of mass, so it will finally end up with ml minus 2 minus t minus. So here you can see we have 6 variables, and out of 6, 4 variables have a same dimension L, and if you come into the MLT system, you can see there is another fundamental dimensions appeared, that is time. Okay, so ml minus 2, t minus 2, ml minus 1 and t minus 2. So that means if we consider in that case the fundamental dimension and the reference dimension, the fundamental dimensions are 3 in that case. That means the total number of variables is 6 and the fundamental dimensions are 3. So in that case, the pi term we will get, that will be 3 instead of 4. So is it possible in a same problem by using FLT system we are getting 4 pi terms, and if we use MLT system in the same problem we can reduce one more variable, is going to be more beneficial, but technically it is not. Okay, because here the reference dimension, basically here t m t minus 2 m t minus 2 is a reference dimensions. So in that case we have a the reference dimension is 2. Okay, so that's why the total number of variable, the total number of pi term will remain same regardless whatever the system you are using. Okay, so there is no benefit to use MLT system, okay, over FLT system. So here the reference dimension is mt minus 2 and the length. So these are the two reference dimensions. So when we minus 6 minus 2, so gonna be 4 pi terms. So in both the cases the total number of pi terms will remain. Okay, so there is no difference in it. Okay, so if we use diameter, so just see how you can continue this whole process. So you will see just change, because the first 4 terms, first 2 terms will remain same. Okay, because is same, you are using delta and you are using h. Okay, so since you are using in those cases gamma and e, so you can calculate pi 4 here, because in the pi 4 you are using the non-repeating variable is e. So sigma pi 4 you replace MLT system. Okay, because here in all the cases, okay, so we are not using any there is no difference if you are using a MLT or FLT system. So anyway, you can carry on the whole problem with MLT system and you would see the total number of pi term, and finally by using MLT system you see the pi 4 you got it e over d gamma, what you got in here. Okay, so that means by using this technique the total number of pi term will is remain same, and the value and the combination of each pi term is also same. Okay, so this is basically the outcome of this problem. Okay, it seems that if you are using MLT system the total number of variable will be reduced comparing to the using FLT system, but technically it is not. Okay, so you must go through all these explanation, so so you would better understand the understanding of problem, understanding to solve this problem. Okay, so let's move on. Here basically the selection of variables. So what does it mean, the selection of variables? To solve any problem, how do we select the total number of variables to solve what are the variables are involved in this problem, what are the variables we should consider, and what variables we should not consider to solve this phenomena or to solve this problem or to do the testing for this particular problem. Okay, to select the total number of variables there is some guideline. Okay, there is a some guidelines to take care of it. So there is no simple procedure to identify the variables to solve any unique or any particular problems. Okay, so we have some guidelines, so we have to rely on the good understanding of the phenomena. First of all, you must understand the problem very well. Okay, involve and the governing laws. Okay, for most of the fluid mechanics problems the variable can be classified in 3 groups. Okay, geometry, that is include length, diameter and angle. Second, material properties, since the external effect like force, pressure and change of temperature depends on the nature of material. Okay, so therefore the material properties that relates the external effect must be included as a variable, just like viscosity, density, surface tension, okay, weight density, specific weight. So all of them are material properties that I have explained to you during the selection of repeating variables. We have a, and third is external effect, and we can also say that this is the flow properties. Okay, the external effect means any variable that produces or tend to produce a change in the system. Okay, so pressure, velocity, gravity, acceleration, force, okay, all of them are the external effect. Okay, the momentum, okay, the torque, all of them are external effect. Okay, so so this third time also, because if you understand a system or phenomena completely, then you will see what are the factors are included in that phenomena. There is another thing: consider other variable that may not fall into one of the above three group or categories, that is time. Okay, so to keep minimum number of variables, it is necessary that all variables should be independent. Okay, all variables should be independent. If you are using a dependent variable, such that we discussed a case, you remember the very first problem we solved. In that problem we discussed that the velocity at the downstream condition is independent variable or dependent variable. So we did not consider that in our in a basic problem, and we proved that this velocity is a dependent variable. So because of that, we did not consider in the list of variables. So let's move on to the uniqueness of pi term. What is the uniqueness of pi term? Okay, so why we are discussing this? Let's see, if a problem involves 3 pi terms. Okay, agar koi, if there is a problem involving 3 pi terms, what does it mean? A new set of pi terms can be formed by combining the above pi terms. Okay, that means you can create another pi terms by multiplying these two. Okay, this is the uniqueness, because the solution, these 3 pi terms, you got it. Okay, it has some combination, numerator and denominator, but if you multiply them together, you will find another new setup of new combination of pi terms. Okay, that means the combination of pi terms we have got by using the dimension analysis, this is not the only shape. You can find some other shape also, and that would be correct also. Okay, so you see, a new set of pi terms can be formed by combining the above pi terms. So if you multiplied these two, okay, so you will get another pi term, that is called pi 2 dash. Okay, so if you multiply this pi 2 dash with first one or the second one, you will get the same pi 1 and pi 1. You see, you are multiplying them together, and you are getting another pi term. When you multiply with the first one, you will get the same number. When you multiply it with the second one, you will get the same number. Okay, and also you see, in the very first example, in the very first practice problem we did, we have selected d, v and rho as the repeated variable. You remember, I think. Okay, in that case we found 3 dimensionless parameters. Okay, so the same case here, so d, v and rho as the repeated variable we selected, and I explained to you also, since it is given in the problem, but we can change. Instead of that, we could select d2, v and mu as a repeated variable as well. So but there is no problem in this solution. But here you see, in the previous example we have selected d, v, rho as the repeated variable, and the pi term in the first or second, in the second lecture, sorry, in the very first lecture we solved this problem of week 7. Okay, so variable, the pi term was obtained, so this was the pi terms we obtained. Okay, the pi 1 we obtained this, and the pi 3 we obtained, this is the value. Okay, but let's see, if we selected d, v and mu, okay, if we selected d, v and mu as the repeated variable, then the pi terms will be rho v d mu into pi delta p d square over mu v. See the difference? Here delta p is d, here delta p v square, here rho v square, here mu v. okay, but this dimensionless number is same, but there is a difference in the dependent variable factor, but there is a change. Okay, so here both results are correct, both results are correct, means there is not a unique set of pi term obtained from the dimensionless analysis, because if you are using this combination, okay, so it doesn't mean that whatever the combination you will use, you will get the same combination. If you change the setup, you might get the different combination, but the net output would be same. Okay, so here, so this is the uniqueness of the pi term, this is the uniqueness of the pi term obtained from the dimensionless analysis. Okay, so however, the previous set of pi terms can be obtained by combining the pi term, as you see, if you multiply this with this, you will get this value. Okay, you see, if you multiplied this and this with a combination, you got the value of a and b. With a combination, okay, you got this value. Okay, here you can see, if you solve them, you will get this value. Okay, here you can see we have two graphs. Okay, the first graph is showing where we selected dv row as the repeated variable, and the dimensionless parameters we got by considering the repeated variable this and this. And when we experimentally describe the relationship between these two dimensionless parameters, we got the graph like this. Okay, because our objective was to determine the pressure drop along the length or per unit length. And when we selected dv mu as a repeated variable, we got the dimensionless parameter these two. Okay, so here when we draw an experimental relationship between these two dimensionless parameters, we got the graph like this. Okay, in the opposite way. But the most important thing is, you see, as shown by the figure here, the resulting graph of dimensionless data will be different. Okay, here you can see for the two formulation of repeating variables. However, when extracting the physical variable delta p, so when you start calculating the value of delta p in both the graphs from the two results, the value will be the same. So the value of delta p will be same. Okay, so this is the uniqueness of the dimension analysis. So dimensionless combination may be changed, may vary, but the result will be same. Okay, so here some common dimensionless here are some very useful and common dimensionless groups we deal in fluid mechanics. So here you can see a list of variables in table 7.1. Here you can see here, okay, the list of variables are mentioned here: the acceleration of gravity, bulk modulus, characteristics length, density, frequency, pressure, speed, surface tension, velocity, viscosity. Okay, so here are the list of variables that commonly arises in fluid mechanics problems. Okay, so fortunately not all of these variables would be encountered in all problems. Okay, because depending on the nature of the problems, nature of the phenomena, the variable changes. Okay, but however, when combination of these variables are presented, it is standard practice to combine them into some of the common dimensionless groups. Okay, that is called a pi terms given in table. Okay, so whenever we deal some practical problems, okay, so some of the variables repeated and some of the variables not repeated, but in most of the cases when the variables are repeated, they form a particular dimensionless groups. Okay, with that we normally see in most of the cases. Okay, so those groups who are repeated in most of the cases are listed here. Okay, and these groups has a physical interpretation also. Okay, these represents a specific relationship, that's why they appear in most of the that's why these groups appear in most of the problems, most of the phenomena. Okay, so here we can see these combinations appear so frequently that special names are associated with them as indicated in the table. Okay, so whenever we know that whenever there is such kind of case or problems, this dimensionless parameter or this dimensionless number will appear. Okay, this we know that based on the nature of the problem. Okay, so it is also often possible, here we can see, it is also often possible to provide a physical interpretation to the dimensionless group, which can be helpful in assessing their influence in a particular application. Okay, so just like this is a very famous dimensionless number that is called a Reynolds number. Okay, so Reynolds number is the ratio of inertia force and viscous force that we will explain in the next lecture, how they become inertia force and viscous force, and generally of importance in all type of fluid dynamics problem. So wherever there is a fluid flow, okay, wherever there is a fluid flow, you will see this dimensionless number will appear there. Okay, so same like the other dimensionless numbers are also mentioned here. Okay, so let's move on. The correlation of experimental data. So what is the importance of correlation of experimental data in dimension analysis? So in fluid mechanics, heavily relies on the experimental data, because we have number of variables and we have to correlate all those variables in a particular equation or particular relationship, and we relate them or we combine them or we developed our equation based on the experimental data. Okay, so dimension analysis helps in interpretation and correlation of experimental data. So this is a technique, dimension analysis, which helps to interpret or make a relationship between the experimental data. However, there are some difficulties in using the dimension analysis. Okay, so how come? Because you see, dimension analysis do not give you any equation. Okay, if you have 6 number of variables in a problem, so it reduces the number of variables, so it reduces your effort. Okay, to perform reduces your effort in the experimental analysis. Okay, so dimension analysis do not give you any empirical relationship, just like y is equals to mx plus c. So it does not give you an equation like that. It always give you the dependent variable is a function of other dependent dimensionless numbers is a function of other dimensionless group. Okay, always it gives the relationship in the form of function of variables. Okay, so here however, there are some difficulties in using the dimensionless numbers. So the degree of difficulty depends on number of pi terms and nature of experiments, how hard it is to obtain the experimental data. So let's see. So problem with 1 pi term. So suppose you have a problem and finally you end up with that, in this case you can only make 1 pi term. So if you make only 1 pi term, then how would you explain this situation? So here you see, if k minus r is 1, then only 1 pi term, because you see the k is the total number of variable, I is the total number of reference dimension. Okay, so here k minus r, if k minus r is equals to 1, then only 1 pi term is required to describe the phenomena. Okay, and the functional relationship with 1 pi term is, so definitely the pi term is a constant. If there is a 1 pi term, so definitely it will become constant. So this is the only case where dimension analysis gives a specific relationship, not the functional relationship. Here you see that I talked just before, because the dimension analysis give you the functional relationship. It doesn't give you a solid empirical relationship, just like S is equals to Vt. Okay, so V 2s is equals to Vf square minus Vi square. So it doesn't give a relationship like that. It always give us a functional relationship between the dimensional group. Okay, so and then we elaborate this functional relationship in the form of experiment. We develop the graph, we develop the line, and based on that we interpret the values of those variables we needed. Okay, so here the value of constant can be determined through experiments. Okay, so example 7.3 you can check. Okay, how exactly they did that. So you must go through your book and see the example 7.3. So what exactly the case. Okay, here assume that the drag force acting on a spherical particle that falls very slowly through a viscous fluid in a function of the particle diameter, the particle velocity and the fluid viscosity. Using dimension analysis, determine how the drag depends on the velocity. So the value of constant for this particular case is already found by Mr. Stokes, and this is also called Stokes law. Okay, so when you will visit this example, so you will understand how he determined the value of constant. So the problem with the two or more pi terms, when you have two pi terms, so if a given phenomena is described with the two pi terms, then the relationship amongst the variable can be determined by varying pi 2 and measuring corresponding pi 1. Okay, so between pi 1 and pi 2 we can draw a experimental curve. So in this case the result can be plotted pi 2 versus pi 1. Okay, however, since it is an empirical relationship, okay, therefore it is valid only for the range of pi 2 covered during the experiment. Okay, so an empirical relationship or an empirical equation can also be obtained by using a standard curve fitting technique. Okay, so when we will draw a curve, so based on that we can make an empirical relationship between those two dimensionless group. Okay, so you can see the problem number, example number 7.4. See your book, just a little bit review it, so you will understand. Okay, so here if a problem with the 3 pi terms, so pi 1 is a function of pi 2 and pi 3, so the data can still be plotted on the graph as the family of curve. Okay, so if you have 3 pi terms, so you see we had same problem when we have the number of variables 4, 5, 6, so it is difficult to conclude. So here now we have a 3 pi terms. Okay, so even then we can plot in the curve. So in x and y we have considered pi 1 and pi 2, and we are varying pi 3. Okay, so pi 3 we are considering a constant, and then we are varying pi 1 and pi 2. Okay, so then pi 3 we change again with another constant, and then we varying again pi 1 and pi 2. In that case we have a combination between pi 1, pi 2 and pi 3, and the best example of this case is the Moody chart. Okay, that we will that it has a very it has a big importance in the viscous flow through the pipes. Okay, so it is the viscous flow is incomplete without the help of Moody chart. Okay, so we will see the application of the 3 or 4 pi terms in a same graph. Okay, so that means it is still possible to develop or a chart which is useful where 3 or 4 pi terms are involved. So as number of pi terms increases, it becomes more difficult to display the result in a graphical form and determination of the empirical equation. Understood? As the number of variables will increase, it is very difficult to make a relationship between those variables by using experimental data. Okay, so for such complication problem, it is feasible to use models to predict specific characteristics of the system. So this is another technique, the models and similitudes, to solve such problems where we have variables more than that, where we have a dimensionless number more than 3 or 4 dimensionless number. So we will see the problem solving technique by using models and similitudes in the next lecture, inshallah. Okay, assalamu alaikum.